All right. Hello, everyone. Welcome to CIERA.
All right. Hello, everyone.
Oh, no, I'm
Welcome
so sorry.
to CIERA. All right. Hello.
I am so sorry. It is muted. Going great. Welcome to CIERA Astronomy Live. We have a great night planned for you all. We're going to be interviewing some astronomers. We're going to be playing some trivia. We have another fun game we're going to do. So while we're waiting for everyone to join the stream, if you could all go to menti.com, we're going to be using this website to do some trivia and also the game in between. So it's menti.com and you use the code 6002480, and then we'll be able to play some trivia while people filter in. I hope you're all very excited for this fun evening. We do have some fantastic people that we'll be hearing from, and just having some casual conversations about astronomy and also what it's like to be an astronomer. And yeah, I think the games are also going to be a lot of fun too. Also, if somebody could put the Menti code in the chat just to make sure that everyone has access to it. Again, it's 6002480. And it's menti.com, MENTI.com. Again, the code is 6002480. Great, thank you for posting that in the chat. Okay. Cool, so it looks like we have a good number of people here. We're going to just wait, make sure that everybody can join in. It's okay if you join late. This is like very low stakes. Nobody's getting any prizes, only glory. So if you join it, you can join in through the round. If you miss a round, you just won't get points for that. Also, you do get points for answering faster. So if you know the right answer it quick. But, a right answer slow is still better than a wrong answer quick, I would assume. So, hey, looks like we have a good group of people. I'm probably going to give it another like 30, 45 seconds, and then we will start. Okay, I am going to start the trivia. Again, answer faster to get more points. So how long is a Martian day? Is it 12 hours, about 25 hours, about 30 hours, or about 45 hours? So a fun fact is the shortest day in the solar system is actually on Jupiter, and it's at about 9 hours. And the longest day is actually Venus, which is about 243 days. So almost a whole year for us, just for Venus's one day. All right. And the answer was about 25 hours. Good job to those who got that. Next question. Okay, so Voyager 1 has been traveling away from Earth for 44 years. How far has it gotten? Is it 2.5 millionths of a light year, 2.5 thousandths of a light year, 2.5% of a light year, or 2.5 light years? And a fun fact is Voyager 1 is due to make its first close pass of another star in 40,000 years. And the close is within 1.3 light years, so still pretty far away. Hey, and the right answer was 2.5 thousandths of a light year. It's hard to know, but good job to those who got it. All right, so currently our leaderboard has Jack in the lead. Good job, everyone. Okay, I'm gonna pause again to let anyone else join in case they missed it. Again, the code is 6002480, and that's for menti.com, menti.com. And it has been posted in the chat as well if you need it from there. This is a great website. I'm very glad that it exists so that we can do these interactive games with everyone here. Okay, I'm going to give it another couple seconds just in case anybody wants to join in or you wanted to go grab yourself something to drink or eat. Okay. Let's do the next question. All right, a secret message was encoded in the parachute that landed the Perseverance rover safely on Mars. What was the message? Was it Curiosity perseveres, dream big or go home, dare mighty things, or we come in peace? So the NASA engineers also encoded the GPS coordinates of the Jet Propulsion Lab in Pasadena onto this rover. All right, and the correct answer was dare mighty things. Very fitting for the rover. Next question. The act of getting stretched apart by the strong tidal forces near a black hole is called spaghettification, Hawking swirly, tidal elongation, or tidal disruption. So even stars can get torn apart like this near massive black holes. In 2019, the Ice Cube Neutrino Observatory detected neutrinos near the South Pole linked to one of these events. So that's really cool. All right, so there was actually two correct answers here. It was both spaghettification or tidal disruption. And it did take that into account if you answered one or the other. So good job. Nobody thought it was the Hawking swirly. All right, and our leaderboard. Ooh, we are having some fierce competition here. Look at that, only 1 point in between Dragonite and Arad the God, 23, nice. Okay, last question. So, do all you can for this one. The projected mission lifetime for Perseverance is 2 years. How long did the first probe to land on Venus last before being crushed by the atmosphere? Was it 2.3 seconds, 23 seconds, 23 minutes, or 2.3 hours? So you can tell by these answers that not nearly as long as 2 years was anything expected to last on Venus. And the atmospheric pressure on Venus is actually 95 times that of Earth. All right, and the answer was 23 minutes. Not long at all, but we got some interesting data from it before it did end up, being crushed. All right, so our final leaderboard, let's see where we're at. All right, Dragon Knight won with 2,817 points. Good job at Dragon Knight. Okay. So now I believe it's time to welcome our presenters and everyone that is involved for today. So if you guys could start sharing your videos and say hi to us all. Great. So I am Genevieve Schroeder. I am a third-year PhD student at Northwestern in astronomy. I study gamma ray bursts and their radio counterparts to them. And Kate, would you like to introduce yourself next?
Sure. My name is Kate. I'm a postdoc at CIERA, and like Genevieve, I study things that explode in the sky, and I also study these stars that get ripped apart by black holes and spaghettified.
Awesome, thank you. How about Monica next?
Hi everyone, my name is Monica. I am, like Jen, a third-year graduate student in the astronomy department. I study binary stars and how they interact with each other.
Great. And then Alex?
Hi, everyone. So my name is Alex Gurvich. I'm a fifth-year graduate student, so, you know, getting up in age, getting those gray whiskers, I guess. And I study star and galaxy formation using supercomputer simulations. And so in particular, what I'm really interested in are how galaxies evolve from just after the Big Bang to eventually turn into things that look like the Milky Way with grand design spiral structure. And so where that spiral structure comes from and how those galaxies stabilize from little explosive clumps a long time in the past is really interesting. You know, so that's what I spend most of my time thinking about.
Awesome, thank you. And Alex, would you like to take it away from here?
I think I can. Thank you, Jen. So we're going to start with our first activity, I suppose, of the night. So we're going to go ahead and move into an interview. So we're going to learn a little bit about Monica's research. But before we do, we want to learn a little bit about Monica herself. So I have 10 questions that she's going to have. How long do we want to give her? A minute to answer? Jen, will you be able to time for us?
Yes, I can do that.
Perfect. So I need like a buzzer at a minute, okay? And this is just going to get us a little familiar, just kind of, you know, get conversation moving, so it's a little easier once we want to start talking science. So if we're ready with the timer, I can start going down my list.
I am ready.
All right, here we go. 3, 2, 1, go. What is your least favorite movie that you've seen twice?
I don't know.
You can pass if you want to go to the next one.
Or I don't have least favorite movies. Go.
Okay. How long is your ideal nap?
20 minutes.
20. That's a good answer. Is it pronounced GIF or JIF?
JIF.
Oh, wrong answer. What's the best book that you never finished?
Rest. I don't even know the title. It's about rest and how we do more when we work less.
Ah, cool. So like nonfiction. What's your favorite meal in Chicago for under $10?
10Q chicken.
Oh, I know, that's so good. I miss 10Q so bad. If you could have, that was the buzzer? Ah, damn. There were some good questions coming up too. All right, so I think we're on a good basis. I think we should move into talking a little bit more about your research and about you in more depth than just 10 cube chicken sandwiches. So, could you maybe just tell us like a broad overview? So you said a little bit about binary stars, but what does that mean? So what is a binary star? Why is that something that you spend all the time thinking about?
Yeah, so binary stars are stars that have a companion. So there's, unlike our sun that just has planets around it, binary stars have another star around it that orbit each other. Um, and I'm really interested in them because they can form into black holes that can eventually coalesce and merge with each other. And I think it's actually really interesting that most of the stars, like our sun, are actually in binaries. They aren't alone. The number is still not exact, but you can think about maybe like 50% of all
Wow.
sun stars are actually in binaries.
So we're almost an oddball. We're like it's where the coin flip. We're tails instead of heads.
Yeah.
Very cool. Um, oh, and I want to emphasize to the audience, if you have questions that you want to hear answers to, please put them in the chat and we're going to go through them. And, the best ones will like sort of interleave with some of the other stuff that we have prepared. So please go ahead, hit the chat if you're curious about something. All right, so we know what a binary star is. And it seems like they're kind of important, right? There's a lot of them. So how do we learn about binaries in general? And more specifically, how do you learn about binaries? Like, so what are we doing? Are you going out using telescopes, like, and counting how many of them, are in pairs?
No, I don't use telescopes. I use simulations, but I do want to give a little bit of some examples of how other people use instruments to study binary stars. So I'm just going to share some slides
Yes,
really quick, and
please do.
hopefully the Zoom YouTube will be on my side. Does this look good?
Yes, that's working.
Okay. Yeah, so I don't observe or study binaries this way, but some people study eclipsing binaries by looking at their brightness. So the brightness is on the plot below the stars, and when the two stars are in our view, the brightness is really high, but when one goes below or in back of the other one, the brightness drops down. And then again, when the two stars are in our view, the brightness goes up and then comes back down. So this is a really cool way to observe binaries. Another one that is closer to what I do is through gravitational waves. So this is something that Northwestern and CIERA are really involved with. So there's two differences here. Instead of stars in a binary, we have two black holes. And instead of light emitting from the system, we have gravitational waves. And this picture here shows one of the gravitational wave observatories that detect the signal when these two black holes collide. So this is much closer to what I'm doing. Or much closer to the stars that I'm interested in. I'm interested in stars that interact with each other, and maybe we'll get a little bit more background to how this happens. But my research, I mostly use computers. You can use simulations to model or simulate, make very realistic movies of what these binaries will do. But more importantly, for my work, I use something called MESA, which is a software that allows you to simulate two systems. So this is a really busy plot, and it makes me feel really cool that I can look at stuff like this, and I look super smart looking at it. But yeah, this is just to give you an example of the types of simulations that I can do with MESA and the types of data that I can get. So I can get the temperature and all of this fancy physics that we can learn from binaries.
So just to clarify, like on your average day, that's what your computer screen might look like, after you have everything run and you have your results. And it's like you're excited, you're anxiously awaiting that screen so that you can start looking at all the different things and find out the answer.
Yeah, that's the part that I get the most excited about. When my simulations work and I'm able to look at all of the data, they're not pretty pictures, they're a bunch of lines, but they do tell me, they do tell me about what's going on with the binaries.
Very cool. So that I think leads into a really great next question. So you were talking about how they interact. What do you mean interact? Because like I know that everything, is kind of interacting with everything, right? It's like gravity goes out to infinity, but it's like, we don't really feel what's going on, from the galaxy next door because the distance is so vast, right? So when you're saying interacting, what is actually happening with these two stars?
Yeah, so I'm just going to share my slides again because it's much easier
Sure.
to show with diagrams. So this is a really nice illustration of what I mean by interact. So I really study binary systems where there's a star and a very massive other companion, usually a black hole. So I don't look at binary systems that have two stars together, but a star and a black hole. And what I mean by what's that?
No, I just said I see. I mean, I was thinking just binaries as like binary stars, but really we can think of binaries as just being any pair of objects, right?
Yeah, there's all types of different types of binaries, which is one of the reasons why this field is so rich and so many different things that you can do. So I have a little illustration of,
perfect.
how what it means for these things to interact and how that even happens. So hopefully people have some idea about the gravitational force. And that's really the key to how these two things interact. So imagine you have two bodies, the yellow one and the black one. The black one is a black hole, and it looks smaller than the yellow one, but it's actually much more massive. So its gravity is going to be much more stronger than a star, like the yellow arrow. And the arrows just represent like how strong gravity is. So
okay, just like the size of the arrow, the bigger black
the size
arrow.
of the arrow. So imagine I put an apple here, and you would think that if I let it go, it's going to go to the yellow point because it's closer, but actually the gravity of the black hole is much stronger, that it will pull the apple if I leave it from there and let go of it. So this is similar to what's happening in this diagram. A star expands throughout its lifetime, and eventually the stuff far away from its center will leave or expand, get close to the black hole, and it can get close enough for it to start being pulled by the gravity of the black hole. And one more cool thing that I want to mention is that you may think that you have like a simple line here between where, an apple or a star's mass will go to the yellow point or to the black point, but actually it's not a line, and it's a much more complicated shape like this. So once the star expands outside of these lines, the black hole's gravity is much stronger, and then you have something interacting like that.
Very cool. So I was just gonna clarify, but then I think you hit it right on the head. Is that so? Your star is gonna start out within that black line, and it's just living its life, being a happy star. But then when stars get older, they turn into red giants. Some do, and then those red giants will be so big that they'll actually get outside that black line, like parts of them will.
Yeah. Yes, that's exactly it.
Very cool. And then those parts, yeah, it seems, I like your little diagram, end up going straight into the black hole.
Yeah.
Very good. So we also have a question from the chat that I want to get to. So is it possible for a planet to orbit to a binary system, whether it's two stars or something else maybe?
Yeah, it's definitely possible. There was a planet found by NASA in 2012 that is exactly that. I think it was the
Oh,
first
wow.
planet ever found orbiting two different stars. It's called Kepler 16b. And it's
16b. All right. So whoever's listening in the chat, go Google Kepler 16b. Go learn more about that. Yeah, so the specific question that they had too was, what does that orbit look like? And I think that that's kind of hard to say, right? Because it certainly depends. But I think the question was specifically is like, is there a stable orbit that looks something like it's swapping between them, and it's like an infinity symbol? Or is it really just that you kind of have two things in the middle and it's going to go around? Or could it like be either or?
it there's a chance for it to be either or, but if you want a system to stay nicely and live long around the two stars without it getting flung out, you're going to want it to be on a nice stable circular orbit so that it doesn't get any like perturbation, so it's like the calmest as possible so that it can stay there as long as possible.
I see. Yeah, so that makes a lot of sense. So even if you find something where it's in some like very complicated orbit, that scenario could be unstable. And so maybe we see it temporarily, but that's not going to live as long as, say, our solar system would. And so it might be harder to find.
Yeah, definitely.
Cool. So I want to go back a little bit to the interaction between the two stars. And so we were talking a little bit about how one star could grow outside this black line and then it would start transferring over to its companion. So that seems cool, but why is that important, right? Like what is that like? Is there something that happens after that? Like what happens to the star that lost all that material? It's like what happens to maybe the black hole that took all that material, so what happens next, right? So you kind of started the story, but where does it go next?
Yeah, so what happens next is basically how we can get the merging binary black holes that I talked about before. So LIGO is really new and it's really exciting, and it's getting all of these observations of colliding black holes, but we have to wonder, where did they come from? How did those black holes get close enough for them to merge? And these interactions that I showed are really one of the ways that you can get black holes that eventually merge. So the stars start off separated, they go through all of these crazy interactions, and if the star is big enough, it could explode into a supernova and leave a black hole. So the black hole we see were at some point,
Okay.
yeah, they were some point stars, and these interactions allowed them to get close enough to eventually form into two binary black holes that will merge. So that's really what I'm the most interested in, these interactions leading to black holes that merge.
Okay, so I think I understand a little bit better. And so is your goal to figure out how, like, which interactions would lead to that, and then say, okay, these black holes in LIGO that we're seeing, we don't know where they came from, but here's a whole list of possibilities maybe, and maybe with some probability that one of them is the right answer.
Yeah, I have a little slide too, showing these
Sure.
the two different scenarios that I am interested in. Yeah, so this is exactly what you're getting at, Alex. There's these interactions that happened, but exactly, what happened after them. So here I'm just going to go really quickly over how we end up with these interactions. So like I said before, you start with two stars up here. The one on the right is more massive, and massive stars explode, and some can leave behind black holes. So now you have that configuration that I'm interested in, a star with a black hole. And when the star expands and goes beyond those black lines that I showed, it's going to interact, like what we saw before. And this is what you were asking. There's different things that can happen, right? So my research is to use simulations to study these two different scenarios. One scenario is that this pulling of the mass from the black hole, this interaction, can be slow and stable, and it'll just remove the outer layers of the star, leaving behind a star that will eventually explode as a supernova and leave behind a black hole that eventually merge. So that's one scenario that I'm interested in. The other scenario is when this interaction is really fast and unstable. And this is something, it's like a theoretical formation channel called common envelope. So the idea is that the pulling of the mass is so fast and so unstable that you actually end up with a black hole inside of the star. So this sounds crazy, and why would people think of this? One of the really great benefits of this mechanism is that after the black hole is sort of inside the star, it can lose orbital energy, the energy that's making it go around and around. It can lose that energy and put it into removing the envelope of the star, this red stuff. And now, similar to the other channel, we have a system where you have a supernova that leaves a black hole, and these eventually merge. So right now in this field of binary systems, the common envelope scenario, this common envelope phase, is thought to be the main reason for why we have these merging black holes. And right now my research and other people in the field is to think, well, is that really what's happening? Can it be that maybe this one is a better way to form them? And yeah, so I use simulations to model these sort of systems.
So that's a great slide. Do you mind bringing it back up?
Oh, yeah.
Because I have a couple questions for it, and we have some chat questions too. So number one, my very first question, I'm just trying to digest it all. So what I noticed, and so maybe this is just like an art detail, and maybe it's not super important, but what I noticed is that on the channel on the left, the size of the black holes are different. But then on the channel on the right, they're more similar.
Yes.
And so my question was, did you do that intentionally? You know, and is it because the black hole kind of ate up all of the mass in that common envelope phase?
Yeah, so I did do that intentionally. So that's a good catch. This slowly and stable mass transfer, it doesn't need to remove all of these outer layers. So you can end up, if the interaction happens slowly, then you only pull on a little bit of the mass. So then you end up with a star that is bigger. And when the explosion happens, you end up with a black hole that is more massive. Whereas on this other end, the idea is that you will remove all of this red stuff. And if you remove all of this red stuff, then you end up with a smaller black hole.
I see. So, sorry, go.
So it doesn't always have to happen this way, but I did it just to kind of give more scenarios for what could happen.
I see. So I guess then my last question before I go to some of the chat questions is, can we look at the black holes that we see in LIGO and say, do we have more that are like about the same size or more that are like one's a lot smaller than the other? And can we say how frequently one of these channels happens with like proportional to the other? It's like, we have 2 times as many emerging black holes coming from the slow accretion versus the too fast. It's like there's not as many just from the ratio of the black hole masses and the number of systems.
Yeah, that's definitely something that people try to do. They simulate these mechanisms for a whole galaxy, and they try to
Oh,
make
wow.
predictions for what the final black hole masses are going to be. So they do their research, they make predictions for what these black hole masses are, and then they compare it to the observations like LIGO. So this is where your question's getting at. So that is possible, but right now there are so many uncertainties in all of this that it's very hard to say definitively which one is the right one or the wrong one. But that's definitely what people want to do in the future. And LIGO is going to keep on detecting more and more black holes. So it's really important that we understand this type of stuff so that we can be able to make those predictions in the future.
So that makes perfect sense. Thanks for explaining it. So all right, so we have a chat question, and I think that this is a good one. So it's kind of a multi-part question, and I'm adding a little bit. So one, is it possible for because what you have here is the binary system exists, but how did we get it, right? So does it happen like that 2 stars form together and they live together forever, or does it happen that there's 2 separate stars that will like zoom past each other and then make friends?
Yeah, that's a really good question. So for the systems that I'm looking at, I assume that the 2 stars were just born together. So stars are born from a really big cloud, and the cloud gets smaller and smaller until you have stars. So the stars that I look at, they just came from the same cloud. There's another way to get binary black hole mergers, which is the other way that you described. You have 2 objects that started from different places, and they're zooming past each other, and they get so close that they become bound. So the people that study this, they usually focus on black holes. So the black holes are already formed and they're flying around in your galaxy or in your star cluster, like a group of stars, and they can get so close and start orbiting each other and eventually merge. So that is also a very valid way to get mergers of binary black holes.
All right, and you predicted exactly what the second part of the question was going to be, is like, what does that whole picture then look like if like we can accept that, you have 2 stars zinging by each other, then what happens? What are all the stages of this happening?
Yeah.
We have another question about planets around circumbinary planets. So I don't know that we're going to be able to answer it. So, but we're going to try, I think. Is it possible, what is the effect on the habitability of a planet to have 2 stars versus one? Is it more or less likely that the planet is gonna be, if it's the right size and everything, that it might be hospitable to life?
Yeah, I'm definitely not an exoplanet scientist, but I also do care about the habitability of stars. My guess would be that as long as the system is stable, as long as it has that it won't disrupt or come apart, then I feel like it probably wouldn't matter too much, because stars like our sun, their life is long. And they're going to remain, similar brightness, similar temperatures for a while. So for stars like our sun, having 2 stars instead of 1 might just be like a simple like addition of temperatures. But that's just my guess. Yeah, do you have any ideas, Alex?
Yeah, so I definitely agree with you. So I think that in terms of the temperature of the stars and the age of the stars, some of the basic parts of habitability, I think it's probably got to be about the same, right? Probably. As long as you're like in this exterior, you have both of them orbiting each other and then the planet outside. Because I agree with you, if you've got one that's like zinging around, who knows what that planet's gonna, maybe it gets eaten. You know what I mean? So that doesn't seem conducive to life. But there's it kind of depends on the question that you're asking, right? Then is like what aspect of habitability. So in terms of like liquid water on the planets, I think it's probably again about the same. The Goldilocks zone is just going to depend on the luminosity of the pair. You just add them together. So maybe it moves your Goldilocks zone out. And so maybe some exoplanet astronomer could say it's like, well, actually, terrestrial planets don't form like that far out, and so now, this is bad. But I don't know that much about exoplanets. The only thing I could think of is, with twice as many stars, you might have it might be the case that your ionizing radiation is a lot higher, and so you end up like the same stuff that would, why we wear sunscreen, would cause cancer or something. That ionizing radiation can be really harmful to life. And so if there's two stars, again, it kind of depends on the situation. Maybe you're closer in or further away. I could imagine that it might irradiate the planet. And there might be a radiation hazard, but certainly this is not my, that those are like second order effects. I think exactly what you were saying, are the big, most important things. There's like just the age of the stars and whether the orbit is stable. I think those are the first questions you have to answer, and I think it's probably the same.
Yeah, it'd be much cooler though.
Okay, so I think that is all of our time for talking about binaries. I want to make sure though, what is the one thing about binaries that you wish everybody knew that maybe you didn't get a chance to talk about right here.
Yeah, I do want to show one thing.
Please do. Yeah, bring it up.
Share my screen one more time. I was super excited when this was announced. I think it was in January of this year. But NASA has found
Oh my gosh.
system. There's no exoplanets here, but there are 6 stars in total orbiting each other. So you have 3 of these pairs that are in a stable orbit around each other. So I was really excited, and I hope that people viewing this are also very excited about this strange system because it's so different from our solar system. It's so different from the stuff that I look at, and here it is.
Yeah, I almost wish, we had more time because I want to hear about how this could have possibly formed, how stable it is. I want to see an animation of all of them spinning around each other. But
Yeah.
this looks incredible. I had not even heard of this TYC 7037891. Beautiful name. Beautiful. I just poetic almost.
Does the system justice?
But all right, I think it is probably good then to move on to the next phase of our evening's activities, which is to play our interactive game. So, Jen, if you want to come back in, and maybe Kate.
Awesome. Yes, that was a great interview, Monica and Alex. Definitely learned a lot. Very cool science happening. So our game, let me share my screen. We are going to be playing a game called 5 Words or Less. And basically, we want you to suggest an astronomy topic in the YouTube chat. I've seen it's been very active, so that's very exciting to see. And you suggest an astronomy topic, and then Alex, Monica, and Kate will all try to explain that astronomy topic in 5 words or less. And we're only going to give them 30 seconds to come up with their 5 words or less explanation. So It'll be very exciting. To do this, you want to go to menti.com again, menti.com. And the code this time is 4690212. And if somebody could put that in the chat to make sure that people can see it, that would be awesome. I'll just give you all a couple seconds to go to this website. So the way it's going to work is, again, you're suggesting the topic in the chat, and then through Menti, you're going to vote on who had the best answer. So I think our first topic is going to be dark energy. Is everybody ready to play?
Oh no.
Okay, so for 5 words or less, I'm starting 30 seconds now. Come up with a description. Go. So we have about 15 seconds left. Again, you will just be voting on other people's answers, on the astronomers' answers. So the participants are not winning this time, unlike the trivia, which we will have more of at the end. And your time is up. So, Alex, would you like to give us your 5 words or less on dark energy?
Total mystery to astronomers.
Great.
That's what I've got.
That's a good one. Okay, how about Monica?
I came up with scary ghost in the universe.
Okay, I like it. And finally, Kate, what was your 5 words or less?
My 5 words were makes the universe expand faster.
Ooh, that was a very interesting one. Okay, great. So now,
very precise.
But I like Alex's too. We have no clue what it is really.
Yes. So on Menti, you can choose your favorite and who you think did the best job at explaining this, or the funniest job, whichever is your favorite, and it is ranking. Make sure you submit it. You do have to click submit, or else the answers won't lock in. So I'll give the chat a couple seconds to lock in their answers. We had some very good answers. I liked all of them. Scary ghost in the universe and total mystery. Neither of those are wrong.
Einstein's biggest mistake or something. I feel like there's something there too. He called it his biggest error. The cosmological constant.
I think ghost is really descriptive because it doesn't interact with a lot of the ordinary matter the same way.
All right. It does look like Kate has a clear lead on that one. So good job, Kate. We will be tallying scores for a couple rounds to see who did the best. All right, so next one, it looks like our next topic is going to be terraforming. So again, I will give you 30 seconds, go. So you're going to find 5 words or less to explain terraforming, which is great because I don't even know if I know what that is. So I would love to know about it in less than 5 words. You have 15 seconds left. These are some great answers in the chat for things that we want them to talk about. Okay, and time. Let's start with our leader from the last round. Kate, what are your 5 words or less on terraforming?
I came up with make planets more like Earth.
That's a good one. Okay, and then how about Monica?
I came up with please be like Earth, please.
Okay,
Please,
I'm seeing
please.
here. And finally, Alex, what was your 5 words?
I'm frustrated because it's almost exactly like Kate's. It's make planets more habitable.
Okay. So we all see a common theme here. This is good. So again, you can rank your favorite responses in Menti, and we'll see who did well this round.
I have to say, the first thing I thought of when the word was terraforming was the board game Terraforming Mars, because that's my favorite board game.
Ooh.
Really? I've never even heard of it. What is
Oh,
just
it's exactly what it sounds like. You play as a different, in the capitalist future, all different companies are trying to compete to terraform the
course.
planet Mars.
it's
And
too
so you
real.
get to do things over many rounds or generations, like, crash asteroids into Mars or
Oh wow.
release microbes that help make the pave the way for other kinds of life eventually, or you can like build an underground city. So it's a lot of fun. I feel like I recommend it to any person who's enjoys sci-fi or
I'm making a note
astronomy.
here for my next board game. Well, post-pandemic, but
There's an
maybe this
online
virtual
version
work.
too, although you have to pay money for the online version. So
Well, I mean, you have to pay money for the real version too, right?
that's true.
All right, it looks like our answers have been locked in, and Alex was the leader in this round. So good job, Alex. I think we're going to do one more round of this, and then we'll move on to Kate's interview. So our final topic of the night is the Big Bang. So I will start your 30 seconds now. Go. So we want 5 words or less about the Big Bang. This has been a very exciting chat. We have had a ton of great answers and wish we could do them all. All right, we have about 10 seconds left for the Big Bang. Can't wait to see what we have. Also, fun fact, all of our astronomers are tied right now, so this will be a tiebreaker round.
Uh-oh.
Winner take all. This is winner take all.
I'm so sorry, let's go back. Let's start with Alex. What was your 5 words?
Oh no, I got a little distracted. The birth of the universe, comma, boom, exclamation point.
Great, that is a good one. And how about Monica? What are your 5 words?
I said big boom many years ago.
Ooh, I like it. Very to the point. And Kate, how about yours?
Mine is simple but boring. I just went with the very beginning.
Okay,
It's like kind of poetic though.
it is.
Yeah, very elegant.
Seems like, yeah, I feel like I'd get that tattooed, like on my wrist or something.
All right, so the chat can now vote on the very beginning was Kate's. So if you want to vote on what your favorite of the answers were. I appreciate Alex's punctuation.
I wanted to be very precise where the punctuation was going.
I like that you both came up with boom as the sound of the Big Bang. I think
It's
that's
very
very
evocative.
descriptive.
Yeah.
I was gonna say explosion, but then I thought someone else would probably say explosion. And
And then we met at boom. So
Yeah.
I'm watching this. I'm very anxious.
Yes, it's very tight round, finding out who is going to win. All right, I think the answers have stabilized, and it does appear that Alex has taken the lead again. So, Alex, you are our winner. Good job at explaining these concepts in 5 words or less.
Thank you. Thank you. I'll accept my sash. Like, just mail it, please. I'll disinfect it when it gets here.
All right, and do you want to move on to Kate's interview?
Yes, it is time for our second interview. So, like Monica, we have some lightning round questions prepared. Let me go ahead and get those up. They are different questions, so
All right.
no cheating. So if you were paying attention, making notes, totally worthless. Not going to help you here.
It's good because I have no idea what my least favorite movie that I've seen twice is.
see, I knew you remembered. All right.
I have the timer up.
All right, then let's do it in 3, 2, 1. All right, here we go. Picture your ideal burrito. Does it have rice?
Yes.
Okay. Name a movie that's better than its book counterpart.
I would say Contact, actually.
That's probably true. I think I agree. How, so okay, in units of pounds, how much cat slash dog slash pet have you owned in your life?
Um, so probably sub 1 pound, although technically they
Oh,
were my sister's pets. My mom's allergic
they
to
count.
cats and dogs, so yeah, small pets
Can you
only.
just say what was that pet?
Gerbils and pet rats.
Oh, I love rats.
They're very
Okay,
smart.
right. Do you pour the milk first or the cereal first?
Cereal.
Okay, yeah, that just seems reasonable. Okay, would you rather fight 100 roach-sized bears or one bear-sized roach? And a short answer, why? As much time as you have.
I would probably go for the bear-sized roach because I think bears are scary, and 100 of them, I don't think I could keep track of
Even
all
the
at once.
tiny little ones, you could squish each one with your foot, like a bear-sized roach. Think of those mandibles. You
Yeah,
know,
but
they could
if I
just
get like powerful enough roach spray, I can stand way back and like spray it at the thing.
interesting. But then at the same time, they have bear spray
Yeah,
that exists, and
but
it's
there's still
very
100 of
powerful.
them. I can't keep. I'm worried about what that 100th bear is
That's
going to
true.
do when
That's
it
true.
hides
They
under
could
my
like
bed and comes to get me in the middle of the night.
the 100th one. You only got 99.
Yeah.
Um,
All right, that was our minute.
yeah, I was figured we were out of time. So okay, I feel like we know you better already. I did not, I feel like my conception of you has changed a little bit. One bear-sized roach, I would not have guessed. Um, so okay, we're gonna start off, I think, on a slightly different foot than we did on the other interview. So I wanted to ask you where were you before you were here at Northwestern? And why Northwestern? What did that path look like? If you could tell
Yeah.
us a little bit about the journey of a hero, the hero's journey, so to speak.
Yeah, no, absolutely. Well, I actually put together a like fun kind of slice of life slide for
Perfect.
what goes on, or some of that shows a little bit of my journey to get to be here. So I think I'll go ahead and share that if that's now full screen. So I think like many people, I got into astronomy because when I was a kid, I enjoyed looking through small telescopes and seeing that you could see all sorts of things up there in the sky. So I put a picture of me and my dad here with my very first telescope. We had it out in the daytime because we were looking at Venus passing in front of the sun a few years ago. But I got, he was an amateur astronomer, so we'd always go out to star parties on the weekends. And at some point, I got very interested in what I was actually seeing, apart from just the fuzzy blob in the telescope. So I started reading about astronomy, and I kind of never stopped. And unlike Monica, who does simulations, I am an observer. So I do go out and use telescopes. I put a picture of me on my very first science observing run. This is back when I was in college. I won't say how many years ago, but and then the picture in the middle is me using my favorite telescope. I primarily do radio astronomy. So I look at radio light coming in from the universe. So, you can think just like it's the same telescope they use in Contact, but I look at things that explode instead of looking for aliens. But I have to say, I did my undergrad on the East Coast, and then I did my grad school on the East Coast as well. I was a grad student at Harvard. And then which is obviously a great place to be. Most of my days in grad school looked very much like this picture. This is me in my office in grad school. Everyone thinks that astronomers spend all their time going out to telescopes, but really we spend most of our time sitting in front of our computer screens, crunching data, trying to figure out what the data all means, writing papers, and occasionally we get to go around and give talks and things like that. So I did my PhD there. And then at the time I was finishing up my PhD, I was deciding where I wanted to go for a postdoc. And there were just a lot of great people doing research in my area at Northwestern, people who were interested in studying these gravitational waves from black holes crashing into each other, people who were interested in studying what happens when a black hole eats a star. I've always really been drawn to kind of understanding the extremes of our universe. And so there's a lot of people at CIERA who are very into various kinds of extreme physics in the universe. So I came here because I wanted to get involved with both of those people, or all of those people at CIERA who do those kind of things.
Okay, that's a perfect segue, yeah, to my next question is so what of those extreme things do you think about the most? Right? So what do you focus on?
Yeah, so kind of the bigger the explosion, the better, or the more extreme, the better. One thing I've been thinking about a lot recently is actually this question of what happens when a black hole consumes a star. So this is a really, really beautiful artist's picture of what it looks like when a black hole consumes a star. I should say that my data are not this pretty. My data looks more
If
like a
only.
single dot on a screen, but it would be beautiful to be this close, although it would also be terrifying to be this close. So you can see there's a so this is the pretty picture, and then this is the little diagram to kind of show what's actually happening in this pretty picture. There's some poor helpless star that gets scattered off of its normal orbit, so it comes very close to the black hole. And because the black hole's gravity is so strong, as the star gets very close to the black hole, different parts of the star get pulled towards the black hole with different amounts of force. And so the star ends up not being able to hold on to all the material in the star anymore. The black hole's gravity is just too strong. So the outer parts of the star start getting pulled away, and the star gets stretched out into this very long stream of gas. And we have a technical term for this process. People who were here at the beginning for the trivia know it's called spaghettification, because you get strung out into a long stream of debris like spaghetti. And that debris from the star, that gas, ends up falling back down onto the black hole, and then the black hole eats up the gas from the star. So while it's doing that, that gas gets very hot, which means it glows very brightly. And so if you're looking at that galaxy where the black hole is, you'll see a bright flash of light. And this is really interesting because normally that black hole is just kind of sitting there not doing very much. It's hard for us to study it if we can't see it. But this flare of light from the gas falling onto the star temporarily lights up this system. So it's like shining a flashlight on this black hole monster hiding in the center of another galaxy. And we can use that light to see what's going on with the black hole. What's the area around the black hole like?
I see. So it's like almost that the star is like shedding light on the black hole. It's just that we kind of see what's happening to the stuff that's illuminated, right? The remains of the star, and we can infer from there because black holes are black, they're invisible. We can't see it.
Yeah, exactly. So just kind of like this picture shows, the black hole itself is dark, but it's the material that's falling onto the black hole, the doomed gas, before it disappears into the black hole. We can see the area right around the black hole that it's lighting up first.
Yeah, and so I have a very quick question here. Why is the light in that weird shape around the, does that mean something, or like what's going on? Like why is it curved?
Yeah, so this is actually really this is actually a really cool picture that they made, and it has some real physics in there. As you get very close to the black hole hole's gravity gets so strong that the light can't escape, which is again why the center is all black. But when you get right near the edge, light starts behaving in this very weird way. It's sort of, you have this light path where the light is almost trapped. And so it ends up getting bent around kind of behind the black hole. So this light that we're seeing, this sort of ring that goes up over the top, this is actually the back side of the disk of material here. So you can see there's like this disk in the front, and it's symmetric. So there's also some material around the back of the black hole. And because of the very strong gravity of that black hole, that light that would normally go out in the opposite direction away from us is actually getting pulled back towards us around the edge of the black hole. So now we're seeing the light from the back of the accretion disk, the back of this gas, and it's getting bent around in this way. So this is actually like, Einstein came up with this theory of how very strong, very massive object would bend light. And they used those equations to predict what this would look like.
Wow, okay. So that bright arch there, you're saying that's the back end of the disk that normally from this perspective we wouldn't be able to see, but it's like kind of being bent away.
Yeah, exactly.
Very cool. So we have a question from the chat. I want to broaden it a little bit, but I want to also answer it directly. So the direct question was, is it possible for a black hole to swallow an entire galaxy? But I think as a broader question too is that, what sort of mass scales are we talking here? Like what sort of things can get swallowed by black holes? So we're starting out with a star. Is that big or small in the grand scheme of things?
Yeah, so these are really giant black holes. And what I mean there is, so, you think of a typical star. If you think of a typical star like our sun, the black hole that will eat the star in this way is usually like at least 1,000,000 times more massive than the star. So it's 1,000,000 times, it's got 1,000,000 times more matter in it than the star does. So one tiny star getting added onto it is not going to affect the black hole too much. And it's actually a really interesting question how the black holes got that big in the first place. So some people think, maybe they've just been eating stars there over the entire history of the universe, and that's partially how they grew so big. And they probably ate stars. They probably ate gas that never had a chance to form into stars. But I don't think they could really eat a whole galaxy in the sense that the black hole is really big, but if you add up all of the matter that's in the entire galaxy, that's still much more matter than is in the black hole itself. So the black hole kind of, it definitely shapes how the galaxy forms, because the black hole is this very massive object. All the stars are pulled toward it. That's why we all end up sort of orbiting around the black hole, if you will. But because we're moving so fast, we're never actually going to fall onto it directly. So I think people also sometimes get scared, that our sun might get sucked into the black hole. That's definitely not ever going to happen. Our sun is moving way too fast. It's going to keep moving around in a circle. And unless it had some drastic close encounter with another star that knocked it off its orbit completely, it's never going to end up getting swallowed by the black hole. So we don't have to worry about that.
Yeah, which is very unlikely, as I understand. So nobody needs to stay up late at night worrying about a close encounter. So I wanted to ask a question. So how long does this whole process take of the star being spaghettified, and how long does the process where we get to see it take?
Yeah, that's a really good question. So the process, so first of all, these events are really, really rare. In a galaxy like our own Milky Way, you'd only expect this to happen once every 10,000 to 100,000 years. So it's a good thing we can see a lot of galaxies out there in the universe, because if we were only watching one galaxy, we probably wouldn't ever see this happen. But the actual process, once it starts, only actually takes kind of a few months altogether. Okay. So the star will come in, it'll get pulled apart, and we'll see this flare of light over a few weeks kind of get as bright as it's going to get, and then it kind of fades away over the next few months. So as the things I study go, it's kind of what I would call a slow thing. But given that, we generally think about galaxies lasting for billions of years, it's actually a really pretty quick process. And it also, it takes longer for a bigger black hole, because the distance at which the star gets torn apart depends on how big the black hole is. So you can learn how big the black hole is by watching how long it takes the light to rise and fade away.
Yeah, so that was you actually answered my next question, which was gonna be, is like, so a couple of weeks, or a couple months, it's like, I've been in quarantine for a year now. That feels like forever, but is that a long time or a short time? And so, I think you addressed that. And I guess, the follow-up question that I had was, if this is a short time in the grand scheme of things, are there challenges associated with observing these things that astronomers aren't used to? Because if astronomers are used to looking at galaxies that look exactly the same for billions of years, all of a sudden stuff is changing really fast. It seems like that might be hard.
Oh yeah, it's really hard. I think the biggest challenge, like I said, is that these are very rare. So most of the time when you're looking at the sky, and you have to look at it multiple times to see something change. So first we had to build telescopes that were big enough to take detailed enough pictures of the sky to be able to see enough galaxies and look at them all the time to check for a change. So that actually is something that we've really only been able to do in like the last 5 or 10 years, is have big enough telescopes doing deep enough observations that we can actually look at enough galaxies to find these things regularly. And then, once you find it, I think the biggest challenge is, it happens and then it's over. So it's sort of like, if you're not there with your telescope ready to swing around and take a look at it as soon as possible, you're going to miss that opportunity. It's never going to come back again. So when one of the, there'll be another one, but it won't be the same event.
Right.
So whenever one of these happens, we really want to start, drop everything else we're doing and switch gears and focus on collecting new data with as many different telescopes as possible. So I said I do a lot of radio astronomy. The radio light from these systems will tell you about a different piece of the puzzle than the optical light from these systems. And these systems also sometimes give off X-rays from the really hottest part of the gas and at the very, very center, right near the black hole. So by putting together all these data from these different telescopes, you really can build up a whole picture. But you need all the data at once. So trying to get that all coordinated can also be a lot of fun. But,
yeah, I mean, it sounds like you need all sorts of telescopes from all sorts of places who are owned and operated by all sorts of different people, all looking at the same thing at the same time. That sounds impossible. It just sounds like it's never going to happen.
Yeah, I mean, it's a lot of fun, though. It does mean that I have collaborators all over the world, which is a lot of fun, except for when I have to get up at, 7 a.m. to talk to them on Zoom because they're in Australia and I'm here. but that part's fun, too.
Yeah. So, all right, I think that is a great segue into another question that we have. Is that, if these collaborators are all over the world, do you ever get the opportunity? And you were saying you get to go to these telescopes every once in a while. So what's the furthest, weirdest place that you've been, that you've traveled to do this, or that one of your collaborators has been, maybe, or whatever?
Yeah, well, I will preface this by saying that, right now, I don't go very many places thanks to COVID, but I think I am going to just answer the question by putting up another slide. I would say both literally and figuratively, this is the coolest place I've gotten to go for science.
Yes, that is probably the coolest.
So
very cool.
Yeah, so this was for a project I worked on in graduate school. There's a bunch of there's a bunch of telescopes down at the South Pole that the U.S. National Science Foundation operates. And the reason they put them down there is because it's very cold and because the atmosphere is also really dry and really stable. And so these telescopes are looking, they're also basically radio telescopes. They're looking at wavelengths of light a little bit shorter than the radio telescope I showed before. But that kind of telescope, the observations will get messed up by too much water vapor in the air. So it's cheaper to put something in Antarctica than it is to launch it on a spacecraft, although they do that too. But that means they need lots of grad students to go down there every Antarctic summer and fix the telescopes and put in new parts and make them so that they can do even better science the next winter. So the telescopes that I went down to work on are in these two buildings over here. Probably it's a little bit small to see on people's screens unless you full screen it on the YouTube. But the other fun thing is fun fact, they do actually have a candy cane striped pole with a little shiny mirror ball on top at the South Pole. So you can go and take your touristy photos and yeah. And then they have a second marker like 50 feet away because this marker they put in and it would be hard. They put it into the ice, but the ice is on top of this giant ice sheet. It's not into bedrock. The bedrock is like 2 miles down. So the whole thing is moving and it moves like, 30 feet every year. So over time, this was at the actual South Pole when they put it in the ice, but now the ice has moved. And so it's, the South Pole is actually like 100 feet off to the side. So then they have another marker that they put on the actual South Pole, which they ceremonially move every year. And it's like a much smaller marker. So it's easier to like pull out and re-put into
very
the ice.
Temporary. Yes.
Yeah.
That sounds like a lot of fun. I guess one follow-up question that I have is like, what was the process like to even just get there? Did you like go in by helicopter? Did you have to take a boat? What?
Yeah, so it's
sounds
actually
like an adventure just in itself.
No, it is. It gave me a lot more empathy and respect for people who, in 200 years ago had to travel somewhere and it, took, because it actually took like 5 days to get there. So the first part of it was just a commercial flight. I got on a plane in Boston and had a couple of transfers and eventually got off a normal commercial flight in Christchurch, New Zealand. And then and then from there are special flights down to the US's main Antarctic base, which is called McMurdo. So you fly in a military LC-130 aircraft, and you get on the plane in New Zealand and you fly down to the main base in Antarctica. And then from there, you wait for the weather to be good enough, which in my case on the way down took a couple days. So I got to hang out on this other station, basically waiting for the weather to be good enough. And then you get in another plane. The LC-130 is specially equipped with skis on the bottom, so it can land on the snow instead of needing a runway, because it takes off on the ice and lands on the snow. And then it's another 3-hour flight from there down to the South Pole Station, which is the second one of the other, the US has 3 main bases on Antarctica. And so the South Pole is a smaller one. So when I was there, there were probably like 150 people on the base. And then for the winter, most people leave except for a sort of skeleton caretaker crew. So there'll be less than 50 people on the station for the whole southern winter. So they'll be there 9 months, can't get in or out, and it's dark for 6 months.
Wow. That sounds terrifying, honestly.
A little too terrifying for me. I mean, I loved getting to go down there, but 1 month in the summer was good for me. I think it takes a really, a really unique, special kind of person to be there for the winter. We had one winter over who stayed there 10 years in a row.
Oh my God, yeah. So
but most people who winter over, they do it once.
Their fortitude. Yeah. Oh my gosh. Well, all right. So that's we have a couple of questions from the chat that are a little all over the place. So I think we can probably just knock them out and call it a night. So number one, is there a limit to how big a black hole can get?
Oh, that's a good question. I think based on the physics we know about, there isn't. The biggest black hole that we know about is probably something like let me see if I can do math in my head, like 1 trillion or 10 trillion times as massive as our sun. And, people are, every so often there'll be a paper, someone will find a slightly bigger one. Those will also be sort of in the centers of very massive galaxies. So that's kind of observationally the biggest that we've seen. We don't know of anything bigger than that, but perhaps there is out there somewhere.
Yeah, I mean, I think that it's like one of these, the edge of the observable universe kind of questions too. Is like maybe there just hasn't been enough time. At maximum rate that these things could grow, because these supermassive black hole mergers take a long time. So you can't even just build them up, so it's just one has to, grow.
Yeah, no, definitely.
Enough.
I mean, I think we don't even really understand how the black holes that, like the black hole in the center of our galaxy, we don't understand how it got as big as it did, as fast as it did. So, it's actually a big question, like how early did black holes get to be, of the hundreds of thousands or million solar masses in size?
Right.
And just how did they do that? Because it does seem like it takes a very long time for 2 big black holes to merge with each other. Exactly.
Yeah. So I don't know, maybe we'll find out soon, I hope. That kind of answers another question that we had from the chat. As more and more black holes are forming over time, is it possible that they're all going to just convalesce into one super black hole that consumes the entire universe?
So I think that's one thing that astronomers used to think was going to happen. It kind of makes sense if you think about it. We know gravity pulls things together. And so it kind of makes sense to think that in the distant future, everything would get all pulled together in one giant black hole. But now we know that everything in the universe is flying apart from everything else. And it's not only just doing that, it's doing that faster and faster. So we can blame dark energy for the fact that probably eventually we will not all end up being pulled together into one giant black hole. But it's a really good question. I think if it weren't for dark energy, it would be very likely.
Yeah, so that's something that I remember reading relatively recently that like kind of blew my mind is that just kind of by it's a definitional thing is that because the density of our universe is right at that limit, right, where we're exactly flat. So that just means that we have, just the right amount of dark energy and just the right amount of normal matter and just the right amount of dark matter and just the right amount of radiation, just the right amount of relativistic particles that once you add it all up, that density is such that the universe isn't going to rip itself apart. It's not going to collapse in on itself. It's just going to kind of keep growing at like a stable pace, maybe I should say. But definitionally, that means that the size of the observable universe is exactly the Schwarzschild radius of the universe, which I thought was really strange. And so there's these, ideas that like, what if our universe is just inside of a black hole, or it's like inside other black holes? Could there be other universes? And with that, we'll call it a night and leave you all to ponder. I guess I want to hand it back over to Jen, and I want to thank both Monica and Kate for being such great interview partners in crime for tonight. And I want to thank all of our audience members for listening to us chat.
Yeah, that was great. Fantastic interview, Kate. The Antarctica stuff seemed very fun. There was a lot of interest in the chat. So we're going to end our night with one last round of trivia. So it's going to be 3 rounds, pretty quick. So, get your points where you can. I saw that is not what I want to do. I am sorry. I saw there was some tough competition in the chat for the first round of trivia. So again, we want you to go to menti.com, and this time the code is 1267025. And again, just 3 rounds of trivia, so it's going to be very quick. Thank you for sticking around and listening and having so many awesome questions for our interviews. It's been a very fun night, and we're very appreciative of how interactive you guys have been. This is our only way to really interact with people outside of our own department these days, so it's glad to see it be such a big success. Great. It looks like we have 17 teams. I'm going to give it just a couple more seconds, see if we have any stragglers. Oh, yep, there was one. Okay. Again, it's menti.com, and it's 1267025. All right. I think it is time to start. So let's go. Again, the faster you answer, the more points you get. Vera Rubin provided some of the first evidence for the existence for dark matter by studying which of these phenomena. So Vera's calculations actually predicted that galaxies should contain like 5 to 10 times as much dark matter as regular matter. And that was met with a lot of skepticism because people just couldn't believe that. But she was proven true after a while, and there's actually going to be a telescope named after her that should be observing this year. All right, and the correct answer was the rotation rates of the galaxies. Yes, that's a tough one, but she figured it out. All right, so our leaderboard so far, John is in the lead. Great job, John. Next question. All right, planets that do not directly orbit a star are called rogue planets, orphaned planets, lone planets, or lost planets. Must be very sad to not have a star to orbit. Probably pretty cold as well. Not somewhere I would want to be. I already live in Chicago. All right. Also, a 2017 study by the Warsaw University Warsaw University Observatory put an upper limit on the number of Jupiter mass starless planets at about 1 for 4 main sequence stars. All right, and the answer was rogue planets. 14 of you got that right. Good job. Let's take a look at our leaderboard now. Ooh, we're getting some competition, aren't we? But John still holds their lead. Good job, John. And finally, last question of the night. Oh, I'm sorry. All right, hopefully that works. Sorry. If you could stand on the surface of the sun, how much more would you weigh than here on Earth? Ooh, this is a fun question. Would you weigh 1 times as much, 30 times as much, 300 times as much, or 3,000 times as much? If you were to stand on the surface of a neutron star, so not our sun, but a neutron star, you would actually weigh about 10 to the 12 times as much as what you weigh on Earth. So if you want to go on a diet, go from a neutron star to the Earth. Pro tip. All right. And the correct answer was 30 times as much. So not as much as you would expect. So let's see how our trivia round went. Okay. We still have John in the lead. Good job, John. You just held your lead the whole time. I'm very impressed. Well, thank you everyone for joining us tonight. And I want to thank our speakers. Alex was great at doing the interviews, and Kate and Monica had some very cool, interesting research that they were talking about. And thank you everyone who showed up and participated. We really appreciate being able to do this with you all, and we hope you come to our future events as well. All right, have a good night and enjoy the sunshine this weekend if you get it. We are here in Chicago.